And what we're going to do is do less of the nomenclature that we've been doing. You've got that down for aldehydes and ketones now, and talk more about their reactions and what molecules they can become by doing those reactions. So to remind you what an aldehyde or a ketone was, they contained this functional group called a carbonyl. Right? It's just a carbon double bonded to an oxygen, the same slide I showed last time. So it's a double bonded oxygen to the carbon, which leaves two other things attached to that carbon. If at least one of those other things, indicated by X and Y here, is a hydrogen, then we call it an aldehyde. If neither of those things is a hydrogen, we call it a ketone. Just a reminder from last time. So what can we do with these aldehydes and ketones? Well, let's see where they fit into our scheme of reactions from our alcohol lecture. And I briefly mentioned this during the alcohol lecture as well. If you start with a primary alcohol and you oxidize it one time, you end up with an aldehyde. Okay? I said it then, we didn't describe what an aldehyde was at the time, but we can now. And if you recall, a very simple way to remember this was if you go from one molecule to another, we call it an oxidation. There are more bonds between the carbon and the oxygen, or fewer bonds between that carbon and hydrogens, or both. So in this case, we're seeing that where we have this carbon, right, has one bond to oxygen in this primary alcohol, right, and then over here in the aldehyde we have two bonds to oxygen. Right? And if we move on to a second oxidation, which aldehydes can do, we get three bonds to oxygen. Right? We'll talk about this molecule later. It's a carboxylic acid. But moving on to secondary alcohols, if we start with isopropanol here as an example, or 2-propanol, it's a secondary alcohol. We can also oxidize it. Again, one bond to oxygen becomes two bonds to oxygen. So this is now a ketone. You notice there's no hydrogens left on this carbon. There was one here, and now there's none. Here we started out with two, became one, and that leaves us one to remove, so we could oxidize it a second time to a carboxylic acid. In the case of tertiary alcohols, there is no hydrogen to remove from this carbon. So oxidation of a tertiary alcohol is not possible. Okay, so you really can just remember that fact, that tertiary alcohols cannot be oxidized, and eliminate it from this chart effectively if you remember that. And that primaries can be oxidized twice, and secondaries only once, because they don't have another hydrogen to remove. Okay? And the same goes the other direction. If I start with an aldehyde, I can reduce it. That's the other direction, the antonym of oxidation. So I can reduce it to a primary alcohol. I can reduce a ketone to a secondary alcohol. There is no such molecule I could reduce to a tertiary alcohol because it can't be oxidized. Equivalently, I have my carboxylic acid, which we'll talk about in detail later, but it can be reduced to an aldehyde, right? Or aldehydes oxidized to carboxylic acids. So if you remember this very small chart, right, it places all these molecules we've talked about, the different classes of alcohols, primary, secondary, tertiary, aldehydes, ketones, and eventually we'll get carboxylic acids in here. So it's a very small chart to remember these states of oxidation. Okay, so a couple of tests for aldehydes, which you'll do in your lab setting, is since aldehydes are so reactive, we can add other components to it and have them oxidize or reduce. Looking at the chart one more time, you notice it can easily go oxidize or reduce from this position. So aldehydes are quite reactive, and that's why they're top of our priority list right now. So one of those tests is called the Tollens test, right? Also known as a silver mirror test. Right? So what you do is you take some solution. It's a silver solution, which you'll use in a lab. It doesn't look silver initially, it's colorless, but it has silver ions in it, right? And if you mix it with your target solution, which you don't know if it contains an aldehyde or not, right? So you mix it with the sample, which you're trying to decide, does it contain an aldehyde? If it does contain an aldehyde, the aldehyde will react with the silver solution. It becomes oxidized. So the aldehyde, this is a shorthand way of writing aldehyde, CHO, right? It means the same thing as this right here, right? The C double bonded to an O with an H still on it. It becomes oxidized to a carboxylic acid, and the silver gets reduced. So in any redox reaction, what you're going to do is oxidize one molecule and reduce another. You're effectively transferring electrons. So when we oxidize this aldehyde, we're removing a pair of electrons, and we give them to someone else. We're giving them to the silver, so the silver becomes instead of a silver ion with a Ag is the chemical nomenclature for silver. Instead of being +1, it goes to 0 as the charge, and that's metallic silver. So it precipitates out of the solution, and it forms along the wall of the container. So if you do this in glass, you'll get a silver coating on the glass. So it's a silver mirror test. That's what it's called. So if you take this silver solution, you mix it with some unknown chemical. If that chemical is an aldehyde, it will produce a silver mirror. Right, so these at the bottom, clearly the first one does not. Second one does produce the silver mirror. So this was an aldehyde in that test, and this one on the right was not. Right, so you do this in lab to determine if certain things are aldehydes, in particular some sugars, which we'll talk about later. Right, another similar test on the same principle is Benedict's test. So instead of using silver here, we can use copper. Right, so same principle though. If there's an aldehyde present, the copper will go from a charge state of +2 to a charge state of +1. So it decreased, it was reduced. And in the same process, the aldehyde was oxidized. So you always have a balance of oxidation and reduction. So if I oxidize the aldehyde, I will reduce the copper. So copper being +2 here, right, or 2+, as a salt with a sulfate here, and it looks blue in solution. So copper sulfate looks blue in solution. When it reacts with the aldehyde here, the copper gets reduced to only a +1. So a +1 copper, it makes two of them bound to an oxygen. This other salt, this copper oxide, which is essentially a copper rust, right, looks kind of a brick red or orange in solution, right? This is what it looks like here, depending on the concentration. So if you have this solution of blue copper sulfate, and you add some unknown liquid to it, if it contains an aldehyde, it will turn orange. And you'll see that with some of your sugars down here as well. Right? So this tells you that this solution contained an aldehyde. So these two do the same thing. This Tollens test or silver mirror test, or the Benedict's test, the blue to orange color change of the copper, both exclusively test for aldehydes. Right? Ketones will not undergo this reaction. Okay, so let's move on to another molecule that you can make from an aldehyde. And instead of just oxidizing it to a carboxylic acid or reducing it to an alcohol, let's do something different. So let's take an aldehyde and react it with an alcohol. So we're mixing two molecules together here. So an aldehyde, which you know that looks like this. Right, it's got my carbonyl group on it, at least one hydrogen, and whatever the other side might be. We're going to call it R for some carbon chain. And we're going to mix that with an alcohol, which this R here, it's written as R prime with a little apostrophe next to it. That just means that it may not necessarily be the same carbon chain as the one here. That's all that means. But it's just some carbon chain, and it's sort of irrelevant what that carbon chain is, because it does not get involved in the reaction. Okay? And of course, it's got an OH group on it, which makes it an alcohol. So if I mix an aldehyde with an alcohol, and there are certain conditions in which this takes place, it needs to be slightly acidic, and you have to remove the water and such, which I'm not going to ask you to memorize. But if you mix an alcohol and an aldehyde, you get something called a hemiacetal. Okay? It's called hemi because it's halfway to becoming an acetal, right? Which we'll describe what that is in a second. Okay, so what's happening here is we're exchanging bonding partners. Right? It's the easiest way for us to think about it, and I want you to remember it. This carbon is bonded to this oxygen twice, and this hydrogen once. Okay? It's going to make a single bond to oxygen instead, so I'm going to erase one of these bonds. That means this oxygen and this carbon each need one more bond. That should make sense to you, because carbon needs 4 and oxygen needs 2. Right? The reaction doesn't actually proceed this way. I'm just explaining the result to you. So this carbon and oxygen are double bonded. I'm going to make it a single bond instead. That means each of them have lost a bond. Right? So the carbon needs one more bond, the oxygen needs one more bond. On the alcohol, the functional part of the alcohol is an OH. There is a bond between this O and this H. I'm going to break that bond and make it, instead of a single bond, make it no bond. Of course, then the O and the H also each need another bond. Right? And they're going to switch partners here. It's kind of like square dancing. Right? So you have your C and your O each break one of their two bonds here. There's still one between them. The O is going to bond to the H from the alcohol. You see the OH over here. And the carbon is going to bond to the O from the alcohol. There's my new bond. So this carbon still has 4 bonds when I'm done. The oxygen has 2 bonds when I'm done. This oxygen still has 2 bonds when I'm finished. And this hydrogen still has 1 bond when I'm finished. But I've switched partners. Right? So if you line these up and think, this carbon is making 2 bonds to O. It's only going to make 1 to this O and 1 to this one instead. And this O, instead of making 2 bonds to carbon, will make 1 to carbon and 1 to the alcohol's hydrogen. And I've split this bond, and I've made this one a single. So I've just rearranged these atoms. Right? So this carbon now has 4 bonds as usual, but there's something new about it didn't have before. It now has a bond to an O with some carbon chain on it. This came from the alcohol, as you can tell. Right? This O is from the alcohol, and this R group, R prime here, is from the alcohol. And this CO that was a carbonyl is now an OH. Right? So it is an alcohol when I'm done, but it also has this other ether bond on it. Remember, ROR is an ether. Right? So carbon, oxygen, some carbon is an ether. So a hemiacetal is kind of halfway between being an alcohol and being a full acetal, which has 2 ether groups. Right? So it's halfway, so we call it hemi, which means half, like hemisphere. Right? So we have an OH group and an OR group on the same carbon. Right? And that's diagrammed here. So there is a carbon with both an OH and an OR on the same carbon. That's all that's required to be a hemiacetal. You notice the hydrogen and the R group that was originally on the aldehyde are still there. They're not important here. They were not involved. They're still there. Nothing happened to them. You could ignore them. Right? And if it weren't an aldehyde but a ketone instead, just below it, it'd be the same thing. So instead of having a hydrogen here, instead of having this hydrogen here, it would just be another R group. Doesn't make any difference. In the old nomenclature, we call that a hemiacetal because it was derived from a ketone instead of a hemiacetal derived from an aldehyde. The more common way to say it is we group both of these together and call them both hemiacetals because they're essentially the same. The R group did not get involved. I don't care if you call them both hemiacetals or if you call this one a hemiacetal and this one a hemiacetal. It doesn't make any difference as long as you know what they are. Right? They both will have the prefix hemi because they have an OH and an OR. Right? So whether you call it acetal or if you call this one specifically ketal doesn't make any difference to me. But don't call them just acetals because they still have an OH. Right? So let me remind you again to summarize that so you know what we're doing here because we're about to apply this. We start with either an aldehyde or a ketone. Right? The carbonyl is the important part of this. The H and R or the R and R are along for the ride. So we have a carbonyl and we have an alcohol. Again, the R group's along for the ride. So all we need is the OH part, the alcohol. These are 2 atoms, and these 2 atoms are the ones that are getting involved. So the CO double bond loses one of its bonds. It becomes a single bond. And the OH that's a single bond becomes no bond. We break it. And these 2 exchange partners. The O here gets the H, and the carbon gets the O. So it's connected all across. Right? So the alcohol becomes connected to my carbonyl, or what was the carbonyl carbon. And the H from the alcohol gets put on this O out here. Okay, does everybody understand that? Have any questions about how this proceeds? I don't care if you know the actual mechanism. If you want to learn that in an organic textbook, they'll go through that with you, the nucleophilic attack and so forth. But it's not part of this course. I want you to see the before and after connections. That's all I really want you to see. So we start with the aldehyde or ketone. The carbonyl is broken. We become just a CO single bond. The alcohol's OH bond is broken. I don't mean the carbon to O bond. I mean the O to H bond is broken. The H from the alcohol ends up on this oxygen, as you see in both cases. And the O bonds to the carbon, making a new connection. Okay? The H and the R, or the R and R, do not get involved. Right? They're not involved at all. So when we finalize this, when we end up with our hemiacetal or hemiacetal, we have a single carbon. Right? The other carbons are not involved, with an OH and an OR on that same carbon. Right? Any questions on that so far?
I'm not really following. I just don't think I understand it.
Okay, what part doesn't make sense?
Pretty much most of it.
Well, do you know what a carbonyl is?
It's an oxygen with a double bond and a carbon,
Right,
right?
so that's the thing in blue here. You can recognize that. And do you remember what an alcohol is?
It's the R group and the OH.
Right, so the part in red here, right? So an OH. I need those two molecules, those two features to appear in this reaction. So one's on an aldehyde, one's on an alcohol. Two different molecules here. And these two are going to interact with each other. The CO, like you said, was double bonded. It's now going to only have a single bond. So I'm going to break one of these, of the two bonds. The O to H bond, which isn't drawn here, there's a line between them, but you know there is a line if you draw it out, right? So the OH bond goes from having one bond to no bonds. I break it. So this reduced by a single bond, and this reduced by one bond. Right? Reduce is a poor choice of words. It goes down by one bond. Right? And this goes down by one. So from 2 to only 1, and from 1 to 0, this bond's broken. Since each of these bonds was broken, those atoms involved need another bonding partner. Right? So in this case, the O out here is going to bond to this H, since they both need one more partner. There it is, the blue to red here. And then this carbon also needs one more bond. It's going to bond to the red oxygen, and that's this new bond here. Right? The H here and the R here, or the two R's from a ketone, here they are again, they're not involved. So in this diagram on the left, I'm showing that. So the R and the H, when I'm done, are not involved. They were part of the original aldehyde. They're not involved in this reaction. But this carbonyl, right, is now an OH. It's not this one. You notice the colors. This CO is this same CO. This H was adopted from the alcohol. And the other bond this carbon makes, the new bond, is to this oxygen. So this bond there. And that's represented here, this OR bond. Does that make sense now?
Yes, it does.
Okay. Any other questions on how this works? I want you to make sure you understand this before we move on. Okay, so instead of having an aldehyde and an alcohol, or a ketone and an alcohol, as separate molecules, let's say, go back one slide a second, let's say this R group down here was some long carbon chain. I don't care how long it is, it's just connected, right? That would still be an aldehyde. And over here, this long R over here would still be an alcohol. It makes no difference to our reaction. We said they're not involved. But what if those two R groups were actually connected to one another somehow? Wouldn't the aldehydes, carbonyl, and the OH from the alcohol actually be on the same molecule? It wouldn't be two separate molecules? That's all I'm changing. The reaction is identical. Nothing changes about it. But when I'm done, since these two R groups, like for this example here, were connected by a chain. So if you want to draw on your slide here, draw a line, some kind of jagged line that connects the two R's here. Then when I'm done, they would still be connected. I didn't alter them at all. But because they were connected initially, and I made this new connection, what have I created? So visualize it.
Ring come around the same carbon, right?
Say again?
They both are groups so that they'd form a ring.
It would form a ring, exactly. So if these two R groups were separate chains, they would still be separate chains over here. And it'd look fine. It'd all be one molecule now. But if these were part of the same long chain to begin with, doesn't matter how long it is or how short it is, if they were part of the same chain, right? They would still be part of the same chain, but I've closed the connection now. I would make a ring, exactly. So these are called cyclic hemiacetals. I'm doing the same chemistry, but my two beginning materials were actually part of the same chain, same molecule. Right? So here's an example of that. Right? If I gave you this name, 4-hydroxybutanol, you should be able to draw that by now. You look at the ending, butane, 4 carbons, so you draw 1, 2, 3, 4 carbons. You may draw it left to right, right to left. It doesn't make any difference, top to bottom, doesn't matter. And then I see the ending, the aldehyde ending, so I know it's on number 1, so I put the double bonded O on there. But it also has a 4-hydroxy, so this is no longer highest priority, right? Aldehydes were higher than alcohols, so this got demoted to a substituent. This is not a carbon, this line is not a carbon, this is carbon number 4. So 1, 2, 3, 4. On number 4, put an OH group. Don't turn number 4 into an OH, then you'd only have 3 carbons. So be careful how you draw that. I've seen that mistake before. So don't do alchemy and turn carbons into oxygens. Draw a bond to the substituent, just like you would if it were a bromine or a chlorine or anything else. Right? So
I have a question.
Go ahead.
Sorry, this may be like that.
I'm sorry, your microphone's breaking up.
Me?
If you're saying something, we can't hear you.
Hello?
Yes.
Oh, can you explain hydroxy again? Does that mean just like an alcohol or?
It means an OH group, right? It's only called an alcohol if it's the highest priority thing. Just like you'll only call it an aldehyde if that's the highest priority thing. That is the highest on your list right now. But as we keep adding to the top of the list, everyone else keeps getting demoted to not as high priority, right? So at some point, if I have an OH group and a carbonyl of the same molecule, one of them gets priority, the other I have to name as a substituent. It's no longer the highest priority thing, right? So in this case, the OH group is named as hydroxy. It's just like naming ethers when you were doing those. If it were a O and then a methyl, you named it methoxy, or 2 carbons was ethoxy. It's just a hydrogen through an oxygen, so it's a hydroxy. Same thing, right? So we name it like it's an ether, but it's not an ether. It's just an OH group, but it's named the same way. If it were a bromine over here, you name it bromoxy, right? Same pattern. So hydroxy instead of methoxy, right? So it's just a way of naming an OH group as a substituent. Does that make sense?
Yes.
Okay. So because it's no longer the highest priority, that's why we did this. Okay, so we've got the molecule named, we drew it, but looking back at our hemiacetal reaction, right? Go back one and look at it. We needed an aldehyde group, right? Or ketone group, so a carbonyl, and we needed an OH group, and we have that. So we have an aldehyde here, and we have an OH here. Now because the R groups are connected, when I do this rearrangement to make the hemiacetal, this is going to make a ring. It's kind of hard to see right now the way I drew it. You likely drew it the same way, maybe left to right or up to top to bottom. But let me rearrange the molecule for you. This is the exact same molecule. Confirm it for yourself. All I did was move the carbons around so I can get this O next to this other O. Right? Specifically this carbonyl, the CO, next to this O. So 1, 2, 3, 4 carbons. Still has 1, 2, 3, 4 carbons. The carbonyl is still at number 1, and the OH is still attached at number 4. It's identical. I just rearranged it here. But you can see how the ring will form now. What did we say would happen? This carbon-oxygen double bond is going to lose one of its bonds and become a single bond. So this is going to be a single bond when I'm done. This oxygen will be bonded to the H derived from this OH. And this carbon will be bonded to the O from the OH. And that's why I rearranged it to put them next to each other. You see I'm going to reform a bond here between this O and this carbon, right? Because this H is going to go over here. So I'm going to make a bond here. That's why I drew it this way. And this H is going to end up on this O as a bond. So if I draw that, it closes a ring. So I've made a bond between the carbon and this O, right? This O is derived from the OH. And this H out here also came from the OH. It hopped on this other oxygen. It's exactly what we did on the previous slide, but the R group that was here, remember I could just wrote R down here, or just R over here, happened to be along the same chain, right? And that means I closed the ring, right? So I don't want you to name this guy. I don't care if you know this name or not, but I want you to know how to take this type of molecule with an aldehyde, or ketone for that matter, and a hydroxy group, right? So it's got a carbonyl on one end, not necessarily on the end, but somewhere. If it's an aldehyde, it will be on the end. And an OH group somewhere, and close the ring. So same partners are dancing. This CO double bond became a single bond. And this OH was broken. This H is no longer connected to this O. And this H is connected to this O. There it is. And this O, which is the same one here, is now connected to the carbon. And there's our new bond. Can I confirm that this is actually a hemiacetal? What was my requirement for a hemiacetal? I needed a single carbon that had both an OH and an OR on it. So here it is. It's got an OH on it and an OR. R is anything other than hydrogen, right? So carbon generally. Right, so OH and OR. Yes, both of those exist on his. This is a hemiacetal. Does it have a ring that involves this carbon? Yes, it's in a ring. It's not a 5-membered carbon ring. It's a what's called a heterocyclic ring. In other words, not all the atoms are carbon. There's an oxygen in the ring. Okay, so but it is a ring, so it's a cyclic hemiacetal because this carbon, which I just proved was a hemiacetal carbon, it's got an OH and an OR, is in that ring. So it's called a cyclic hemiacetal. Okay. Here's another example down here. Right, it's the same one. I just take this one and turn it. It's the same molecule, so it may not always be written this way. But this is a hemiacetal carbon for the very same reasons. It's got an OH and an OR on the same carbon. Right, and it's in a ring, so it's called a cyclic hemiacetal. The one on the right here is very similar. This carbon has an OH and an OR on the same carbon, so therefore it's a hemiacetal, but it's also in a ring. This other appended ring has no bearing on that. It's just a bigger hemiacetal carbon, right, or hemiacetal molecule, but it's also cyclic. If this carbon did not connect in a ring out here, and this ring was still here, it would not be a cyclic hemiacetal. So imagine these carbons weren't here, right? It would just be a ring as a substituent on this thing, and it would not be cyclic hemiacetal. So this carbon must be involved in a ring to call it this. Right? So I threw a picture of it here on the top left for you to remind what a hemiacetal is. The R doesn't matter what it is, and in fact these R's could be connected. That would make it cyclic. But it needs an OH and an OR on the same carbon. So I'm going to throw some examples at you, and you decide yes or no, is it a hemiacetal? Right, so let's draw this one first. It's called 1-ethoxyethanol. I'll start with the ending, 2 carbons. Ethanol indicates it's an alcohol. So I'm going to draw a 2-carbon chain, and on one of the carbons, put an OH group. I don't mean turn one of the carbons into an OH, because that would just make methanol. That's alchemy. You can't do that. Right? So I'm going to write a 2-carbon chain. That's just a line, right? It has 2 ends. I put an OH on one of them. So off of that, I will draw an OH. So here's my line. Right? 1, 2 carbons right here. 1, 2. And off of number 1, I put an OH. Also on number 1, that's what this means. I'm going to put an ethoxy. That's a 2-carbon chain connected through an oxygen. This is an ether linkage. So here's 1, 2 of my main chain. 1, 2. I put an OH on number 1. And then off of number 1, I also put an O with an ethyl group on it. So this is an ethyl group attached through an oxygen. So this is an ether and an alcohol. Right? That's why it's named this way. The alcohol's priority, so this ether is just named as a substituent. Okay? Is this molecule a hemiacetal? Yes or no? Does it fit this pattern?
Yes.
Yes. There is a carbon that has both an OH and an OR. So yes, this is a hemiacetal. It fits that pattern. All right, the next one. Let's try 2-ethoxyethanol. Right, so ethanol, again, a 2-carbon molecule with an OH on one of the carbons. Whichever one you put it on will be number 1. And then on the other carbon, number 2, put the ethoxy. So here I drew it again. 1, 2. I happen to draw it left to right, or right to left this time. 1, 2. I put an OH on number 1. This means that's number 2. And on number 2, I put my ethoxy this time. Right? It doesn't matter if you pointed it up, down, left, right. Doesn't matter, as long as you make the right connections here. Right? So is this a hemiacetal? Does it fit that pattern?
No.
No. That's right. The OH and the OR are on separate carbons. They're not on the same carbon like this one was. So this is not a hemiacetal. Okay, how about this one? I told you didn't have to know this name, so I'll draw it for you. It's 2-tetrahydropyranol, so it looks like this. It's a 6-membered heterocyclic ring with an OH on it. So you don't have to know this name, so don't worry about that one. But you should be able to recognize this as a hemiacetal or not. Which one is it? Yes or no?
Yes,
Why?
Yes.
because it's on the same
The
carbon.
O and OH are connected on the same carbon.
Right, so the OH and the OR are on the same carbon. Can you be more specific? But yes, it's a hemiacetal, but can you be more specific?
It's a cyclic hemiacetal.
It's a cyclic hemiacetal. Not because it has a ring, that doesn't make it correct, because the carbon that you decided was a hemiacetal carbon is in that ring. Right? So yes, it has to have a ring, but if it were just a ring sticking off the side somewhere, it wouldn't make it a cyclic hemiacetal. So the carbon you were deciding, yes or no, is in that ring, and you decided yes it is, because you were correct, it's got an OH and an OR, but it's in that ring, so it makes it a hemiacetal, and more specifically a cyclic hemiacetal. Okay, how about this one at the bottom?
How come?
Go ahead.
When you say OR, like what is the R that you're referring
R
to?
means some carbon chain. It doesn't matter how long or short it is. It's just not a hydrogen, right? So in these cases, when I'm saying OR, the R is just some other carbon chain. For example, in the first one, this was not an OR, it was an OH. Whereas to the left, I have O, not an H. So I'm going to call that an R group. Just means not a hydrogen, right? Generally some carbon chain.
And then why is the second one exactly not an...
Okay, so the second one is not because our requirement was to have this OH and the OR on the same carbon atom. Here, the OH is attached to this carbon, number 1, and the OR is attached to this carbon, not the same one. All right, they're neighboring carbons, but they're not the same one, so that's not a hemiacetal. Whereas in these other two cases, both O's are on the same carbon. Do you see that? Here, the O's are on separate carbons.
Okay, thank you.
Right. It's really that simple. You just got to follow this pattern. That's why I threw it up here in the corner for you. Right. The next one. Let's try naming this thing, or drawing this thing. So we start with 1-propanol. How long is that?
3.
3 carbons. So try drawing this with me. So draw 3 carbons. So that would be 2 lines, right? So you start when you put your pen down. That's number 1, 2, 3. Okay. So draw that. What does propanol mean?
Alcohol.
So what do I draw?
H on it.
Draw an OH on it, and where should it go? I have 3 carbons to choose from.
Number 1.
On number 1. So not the middle one. You can put it on either end, but whichever one you put it on will be number 1. Right? But don't change your numbering system once you start drawing. If you draw 1, 2, 3, stick with those numbers. Right? So let's put it on number 1. Then also on number 1, I need you to draw something else. What is this?
Methoxy.
What does that mean? What does it look like?
There's like O and 1 methyl.
Right, so connected to number 1. Right, so here's my 1, 2, 3. You may have drawn it up instead of down. Doesn't make any difference. So 1, 2, 3. You guys threw an OH on number 1 just like I did. But also on number 1, I put an oxygen with a methyl on the other side. Not a methyl and then an oxygen. That would have made the chain longer. That is not a methoxy. Methoxy is the carbon attached through the oxygen. These carbons are not connected. Right? So here's my methoxy on a 1-propanol. Is this a hemiacetal?
Yes.
Yes. And what makes it that?
Because the
They are all
OH
on the
and
same
O are
carbon.
on the same carbon.
Right, so both, you're right, both oxygens are on the same carbon. Exactly, one's an OH and one's an OR. You're going to start to see it in the names themselves, right? So ethanol, by definition, the OH is on number 1, right? There's only 2 carbons to choose from. And look where the other thing is. This OR, which is what ethers are, is also on number 1. The name could have given this away. This one, they're not on the same carbon. Could have given that away. Here they're on the same carbon. So the names are going to start to give it away for you before you even finish drawing. You should suspect the answer already. Right, so how about the next one? Before you draw it, let's try to predict what it'll be. And then we'll draw it and confirm.
It will not be.
Why do you think so?
There's 2
Because the
propanol.
methoxy is on 1 and propanol is on 2.
Right, so the OH is on 2, and the methoxy, which is the OR group, right, is on a different carbon. So you're absolutely right. So if we draw this, we got our propanol, 3 carbons once again. So 1, 2, 3. We put our OH here. And on number 1, don't write an O here because it's a very common mistake I see. When you drew your propanol, you went 1, 2, 3. You put your OH on number 2 like this, great. And then when people start drawing these, sometimes I see this, when they draw the methoxy, they just write O right here. They turn number 1 carbon into an oxygen, which is not what you should be doing. You should be drawing a bond to that O. I didn't add any more carbons here, I just drew a bond. And then on the other side of the O, I put the methyl group, right? If you make that mistake and write the O here, it's going to look like a hemiacetal when you're done because you didn't draw this correctly. But I'm assuming you guys did draw this correctly now. 1, 2, 3 carbons, OH on 2, methoxy on 1. And like you predicted, they're not on the same carbon, so this would not be a hemiacetal. Right, and finally this one.
Professor?
Go ahead.
Just for clarification, so just by reading the name to declare if it's a hemiacetal and whatever the parent chain has.
So I think we lost you there before you could get your question finished.
Can you hear me?
I can now.
Right, when you're just going to declare the ethoxy or methoxy, whatever it is, does it have to be the same number as the parent chain?
So in the name, you generally, sometimes you tell where the OHs are, if it's generally a longer chain. If it's short, like ethanol, you don't have to tell me where they are, right? Because it's automatically on number 1. So if you look at the locators for these names, generally the OH is located and the methoxy or ethoxy or whatever ether it might be are also located. So if they're on the same number, you're pretty certain that it's going to be a hemiacetal, right? And if they're not on the same number, then it's likely to not be. There are some weird scenarios where you actually need to draw it, such as when you have ethanol, because you don't really know if it's going to end up on the same one until you draw it, or if you have some rings or things like that, where the OH is not explicitly shown the number, but it's an implicit, you know where it is. Does that make sense?
Yes, sir. Thank you.
So on the last one here, you guys work this one out, and I'll help walk me through it. Is this a hemiacetal?
No.
No.
I don't think so.
Why not?
Different carbons.
Are they?
Different carbons.
Or is there a mistake in this name? Let's
Wouldn't it
try
depend
drawing
on
it.
where you put the hydroxy?
What was that?
I mean, wouldn't it depend on where you put the OH? Because you can either put it on 1, and that could be 3, or you could either put it on the other end, which also could be 3.
Could it
So
be 3?
wouldn't it depend?
Could it be on 3? Or no matter which end I put it on, it's going to be number 1?
It says propane, the number 1.
It's going to be on number 1 no matter where I put it, right? So here, if I try drawing it like I have here, right? So I wrote 1, 2, 3, and I put the OH here on 3, right? And then drew a methoxy on 1. And from the name, this is what I intended to draw, because they're clearly on different carbons. So you're right, it's not a hemiacetal, but this is not the correct name. So it is not a hemiacetal, but this name is wrong. What's wrong about it?
The OH has to take priority.
The hydroxy group has priority, correct, over an ether. Ethers belong in the everybody else category, right? So what should this be named? So this should be number 1, right? So it should be a 1 propanol, yes.
Maybe
One.
And
methoxy 1 propanol.
So it'd be a 3 methoxy 1 propanol, right? So this name is incorrect, right? So make sure you correct that in your slides, but it's still not a hemiacetal because they're not on the same carbon. But the name is incorrect, and I wanted to point that out so you don't get confused by some of these. When I write them this way and ask you to correct their names, keep in mind what has priority. So this is a 1, 2, 3, so it should be a 3 methoxy 1 propanol, exactly. Okay, let's move on to the next part. Since you kind of have hemiacetals, you've got a grasp on that now. What I'm going to do is take your hemiacetal, which, remind you again, has an OH and an OR on the same carbon, and I made it from an aldehyde plus an alcohol, and I'm going to add yet another alcohol. I'm going to add a second alcohol, and we're going to play the same game. So if you remember, if you go back 1 second to these guys, right, we started out with a carbonyl which had 2 bonds, right? We subtracted one of them and we left 1 bond. we had an OH group with a single bond between them, and we subtracted one to make it no bonds, and we exchanged bonding partners. This carbon now bonded to the O, and this oxygen bonded to the H. Okay, and that made us our hemiacetal. So we're going to do the same thing again. We're going to start with the hemiacetal this time and add yet another alcohol. Okay, so I'll show you here real quick and then I'll go back to the other slide. So the same CO bond that was originally a carbonyl and is now a CO with an H on it, this we're going to subtract another bond. Right? So this is going to go from one bond to no bonds. We're going to break this bond. Right? So this carbon is going to need another bonding partner. And the next alcohol that shows up, let's say this is the next alcohol that shows up over here, I'm going to break that OH bond once again. And the H, once again, is going to go on this O, and the O is going to attach itself to this carbon. So this carbon is going to acquire a second OR group. Does that make sense? Because I'm breaking this bond, it's going to go to 0 bonds here, and I'm going to break this bond like I did before from the new alcohol, and this O is going to attach itself to this carbon, making yet another OR group. And since this bond is broken, and this O is going to get this H, what will this become?
H2O.
H2O is going to become water, exactly. So when we add that second alcohol, right, which is down here, right, so starting with the carbon here, which had one OR and one OH perhaps here, right, I'm going to break that bond. This left as water, and the new alcohol became an OR group. So unlike a hemiacetal, a full acetal isn't halfway. It has 2 OR groups. It doesn't have its OH anymore. It left as water. So in that hemi, we're all the way there now. We have an acetal, which has 2 ether bonds on the same carbon. So 2 ORs on the same carbon. Now you notice the bottom side of those things, the original aldehyde or the original ketone, where it had an H and an R over here, right, shown here, they're not involved at all. Right, so they're still there. Here's the R and the H if it started out as life as an aldehyde, or the 2 R's if it started as a ketone. They're still there. They've not been involved the entire time. So now we've replaced the second bond between the carbon and its original oxygen had 2. We went down to 1, and now we have 0. It's gone. We have 2 OR groups left. Okay, so can you pick out acetals from a lineup now? Just look for 2 ORs on the same carbon. That's all we're doing. So just like before, if my next alcohol that shows up was actually connected to the original chain to start with, I'm going to get a ring. So same thing as before. So here I have a hemiacetal on this end. So confirm that for me. This was made. It's a hemiacetal. There's a carbon with an OH and an OR, whatever it might be over here. This is a hemiacetal. And then it also has an alcohol group elsewhere in the molecule. Right, so I'm going to play the same game. This OH bond is going to go to no bond. Right, so this bond is going to get broken. And this O to H bond here is going to get broken. Right, this H is going to end up with this O to leave as water. You notice this is going away as water. And this carbon is going to make yet another bond to this O. So I'm going to close a ring. Right, there's going to be 2 O's in this ring this time. Okay, so if I rearrange this, draw it slightly differently, same molecule, I've just redrawn it. Right, so this I've flipped upside down, right? This carbon is that carbon, this carbon is that carbon. I've just rearranged it such that when this OH leaves right here, right, this OH, this bond is being broken, right, it's leaving, and this O over here is being reconnected, or if you want to think of it as, this is the carbonyl, or sorry, this was the hemiacetal carbon, it's equivalent, OH, OR, either one, right, and this leaves, I'm going to make a ring here. So if I do that, this water leaves and I close this ring. Right, so I have a new connection here, and this carbon now has 2 OR groups on it. They happen to be the same R group, so it closed into a ring. So instead of calling it a hemiacetal, it's just an acetal, and because this carbon is now in a ring with 2 O's, we call it a cyclic hemiacetal, or cyclic acetal, sorry. A byproduct of this reaction is the water that left, and answer this question. Where did this O of the water come from originally? If I go back to when it was originally an aldehyde, where did this O come from?
From the OH?
Well, it was from the OH of the hemiacetal, but where did that OH originate? Where did the O of that originate?
In the carbonyl.
It was the carbonyl oxygen, right? It was that double bonded oxygen. So that double bonded oxygen was originally only bonded to the carbon by 2 bonds. When we made it into the hemiacetal, it only had 1 bond left to that carbon and 1 to a hydrogen. And when I go to the acetal, it has no bonds left to the carbon. We cut it off and 2 bonds to hydrogen. So this water's O was the original carbonyl oxygen, right? And both of the bonds that carbon was making to it has now been replaced with bonds to other O's, the O's of the alcohols I've added, or the OH groups if it's in the same molecule. Okay.
I have a question.
Okay.
It was easy for me to see it. How do you pronounce it? Hemiacetal.
Uh-huh.
It was easy with the different colors. I'm not seeing where they're going.
So try drawing these with different colors as well, and we can do that after class if you want.
Okay.
So let's try to identify them first, and then we'll after class we can put them together. So here at the bottom, all right, is this a cyclic acetal? So what's required to be an acetal one more time? I need 2 ORs on the same carbon. Does this carbon qualify? So I have an OR here, and I have an O methyl, that's an OR here. Yes, this carbon qualifies. Is this carbon in a ring? Yes. So it's a cyclic acetal. It may have 2 O's in the ring if they were both on the same molecule. It may have only 1 if they were only 1 on the same molecule. Okay. This one here is also a cyclic acetal because it's got 2 ORs on the same carbon, right? As does this one. It's got 2 ORs on the same carbon. Okay, so all these are acetal carbons. You notice it was a hemiacetal if it still had at least 1 OH left. But it's
Can
got...
you explain?
Go ahead.
It's like 2 ORs,
You had
like on the left.
on the left.
Mm-hmm.
How is this one 2 ORs? So the top
Yes.
part is an O and then some carbon chain. And the bottom is also O bonded to some carbon chain. That's all.
Okay.
That's all OR means. R just means carbon chain. So O carbon chain, O carbon chain. Okay. So let's play our little game one more time. Here, remind you in the top left corner what an acetal looks like. 2 OR groups on the same carbon. The other things don't matter, right? So is this one an acetal? So let's try drawing it. So draw propane first. So you're going to lay down 3 carbons. And on numbers 1 and 2 of your propane, you're going to put 2 ethers, right? So dimethoxys. So here's my propane. I drew it 1, 2, 3, right? So 1, 2. You could have drawn it 1, 2, 3 the other way. Just same thing. So 1, 2, 3. And on numbers 1 and 2, I put O methyls. O methyl. That's what methoxy is. And there's 2 of them. Is this an acetal?
No,
Why not?
because
They're not on the same carbon.
The different carbons.
They're on separate carbons, right? So one of them's on number 1 and one's not on number 1. Right? That's all this means. So again, the name should be sort of giving these away. Okay. So how about the next one? Draw ethane first, right? 2 carbons. And I need a methoxy on number 1 and an ethoxy also on number 1. Right? So I'm going to draw ethane. Here it is on the middle of the screen. So 1, 2, going straight up. 1, 2. Right? And on number 1, I put an ethoxy on the left and a methoxy on the right. Right? So the main chain here is this vertical thing. 1, 2. Is this an acetal?
Yes.
Yes, and the name sort of gave it away again. Right? So there's an OR and another OR on the same carbon. It doesn't have to be part of the main chain, all those carbons I'm talking about. That's how we named things. But as a whole, there is a carbon with 2 ORs. That makes it an acetal. Okay, so good. That one's correct. How about the one on the right? Excuse me. So we have cyclobutane. So we draw a 4-membered ring. It's just a square, right? And on numbers 1 and 2, put methoxy groups. So it should look something like this guy. So you draw a square. Wherever you draw your first one will be number 1, and then draw number 2 next to it, not across from it on number 3, but 1 and 2. Is this an acetal?
No.
No. Once again, they're on different carbons. Right? Good. So these should be getting easy for you at this point. Okay.
Wait, I have a question.
Go ahead.
Why can it be like both in the ring and out of the ring?
What do you mean both in and out of the ring?
Huh?
I don't understand.
Sorry, excuse me. Wait, I can't hear you.
Yeah, you have a lot of background noise, but I can't understand your question. What do you mean in and out of the ring?
Like for the last slide on the. Can you hear me?
Yes.
Okay, for the last slide on the left, it could be like the one of the ORs outside the ring.
On the left?
How come like that's allowed, but like in other stuff it's in or out of the ring?
So the one on the right here, the main chain is the ring. That's how we get cyclobutane. And these other things are substituents. They're not part of the main chain.
Yeah.
So I don't
Okay, never mind.
Okay,
It makes sense.
let's try the one at the bottom here. So we have methane, right? That's just a dot on the page, right? You don't draw a line for methane. It's just a dot. It's one carbon. So just make a dot on the page with your pencil. And then on the methane, I need to put 2 of something. There's no numbers here because clearly they're both on the one carbon that's present. So I need to put 2 cyclopentoxys. That sounds complicated, but it's not. It's a cyclopentyl group attached through an oxygen. So I put a dot on the page. Here it is in the center. And I put a cyclopentane ring attached through an oxygen. And then another over here attached through an oxygen. That's my dicyclopentyl groups attached through oxygens, so dicyclopentoxy, and attached to my one and only carbon of the main chain, the methane. Is it an acetal?
Yes.
Yes. Once again, both OR groups, the R groups are quite large here, but it doesn't matter what they are. They're R's, so I have 2 ORs attached to the same carbon. They don't need to be the same R groups. They are in these last 2 examples, but in this example in the center, they were separate R groups, right? One was an ethyl, one was a methyl. It doesn't matter what they are, as long as they're ORs. Okay, so this one does qualify. Right? And one more on this page, a 1-propoxy ethanol. So let's draw that. We draw ethanol first. That's 2 carbons with a OH on it, right? That's the OL, alcohol ending. So I drew 1, 2, vertical again. So 1, 2. On number 1, I put an OH. And also on number 1, I need a propoxy. So that's an oxygen with a propyl group attached on the other side. Is this an acetal?
No, it's a hemiacetal.
Right, it's not an acetal, it's a hemiacetal. These aren't 2 ORs, it's an OR and an OH. This was my hemiacetal, exactly. Okay, good. So instead of building these things, which you're very familiar with at this point, let's start with one of them that you can identify as an acetal and reverse the process. Let's tear it apart. So remind me how we made these things again. We started with an aldehyde or a ketone, which had that carbonyl, and then we added an alcohol, which resulted in a hemiacetal. Then we added yet another alcohol, and that resulted in a full acetal. Right? And along the way, our carbonyl bond went from 2 bonds to 1 bond to no bonds, and the O left as water. Okay? So if we start at the end with an acetal, and I add some water, I'm going to do hydrolysis, which is hydrolysis. It's the breaking, that's what lysis means, of a molecule using water in this case, so hydrolysis. If I add water back, I just reverse the process. So if I start with an acetal, and I add water, I'm going to add a bond between the water's O and that carbon, the acetal carbon, the one with the 2 ORs on it. And I'm going to break off one of the ORs, and it's going to result in an alcohol that leaves, right, with one of the H's from the water. And I'll show you some pictures of it in a second. And then if I add yet another alcohol to it, it's going to break the other OR off, right? Or sorry, not add, but I remove the other alcohol as an OR, and I make the carbonyl back. Right? So I'm reversing the process. That's all I'm doing. So let's do a quick example so you can visualize what I'm saying. So the one at the top here, right? I'm going to start with this molecule. It's one we just talked about. It's the 1-ethoxy, 1-methoxy ethane. So ethane here, 1, 2. This is the acetal carbon. It's the one you're judging, right? It's got 2 ORs on it. That carbon will eventually become the carbonyl of the aldehyde I end up with. And so the carbonyl is the same as the acetal carbon. They're one and the same. So this is the important carbon I'm talking about. The 2 ORs are the things that are going to leave as the alcohols. So I'm adding water to this. Right? So if I add a water, if you can draw out a water molecule right here. Right? So write an O with 2 H's on it. Right? I'm going to take this carbon and the water. They have no bonds between them currently. And I'm going to make one bond between them. Between this carbon and the O of the water. Right? I'm remaking a bond there. That means the water needs to lose one of its H's. Right? So it loses an H. The H goes on this O. And I break this bond because this carbon made one to the other O. So I'm undoing my formation process. So break this bond. This is now an OH. It's ethanol. And it's free to go. Then I make a second bond between this carbon and the water's O. Right? So now I have a double bond here. It's a carbonyl. And the other H from the water goes on this O. And this leaves as methanol because it's only one carbon long. So I get an ethanol and a methanol back. And then I have a 2-carbon group here that's double bonded to an O. That's a 2-carbon aldehyde, right? Which would be an ethanal. Right? And that's what's shown here. I end up with my 2 alcohols that are peeled off as ethanol and methanol. And then the 2-carbon piece in the middle is still there. And this O came from the water. Right? So this O was the water I introduced to break the system. It started out with no bonds to the carbon. We made one, we cut off one of the alcohols. We made a second, we cut off the other alcohol. Where did the water's H's go? They went on the alcohols. Here it is. So here's your water you added, the O, H, and H. Right? So we split apart the water to do this. Right? That's why it's hydrolysis. We're using water to break bonds. It's exactly the opposite of the process we just described, where I started with this and added the first alcohol. Right? Remember, the H would go on this O, and this O attaches to the carbon. Then I add the second one. This H goes on the O. This bond would be gone when it leaves as water, and this O attaches to the carbon. That'd result in this. So this is exactly the opposite of building these acetals, is tearing them apart. And it's called hydrolysis. Right? You do the second one with me. Add a water molecule right here. So add a water molecule, put an O and 2 H's on this thing, right here or below. It doesn't matter. Just draw it here somewhere. Right? And start building this carbonyl. So we have no bonds between this carbon and the water's O. So draw one between it. That means the water needs to lose an H. The H is going to go on this O, and I break this bond. Right? Do it again. Draw the second bond between this carbon and the O. The water has to lose its other H. It goes on this oxygen, and there's our second alcohol that leaves. So I'm going to get 2 identical alcohols because these were the same. And what will the name of that alcohol be?
Pentanol.
Cyclopentanol, and I'd actually get 2 of them, right? So I'll put a little 2 in front of it in the reaction. So I get 2 cyclopentanols. How long will the carbon chain be that's left behind? If both of these alcohols leave, how long will the carbon chain be that's left behind?
One.
Just the one carbon, right? The methane that's there. Just like this ethane became ethanal, what will the one carbon group become?
Methanol?
Not methanol, but methanal, right? It's going to be an aldehyde, right? So if I do this, I'm going to get the methanal, so it's a carbon double bonded to oxygen. There's only one carbon left, and both of the alcohols leave, just like before. It's exactly
Where's
the opposite.
the hydrogen in there for it to be the aldehyde? I don't.
So this carbon has 2 H's on it. They're just not drawn. Just like this carbon here has an H on it. Right? It's still there. It's never gone anywhere. The 2 things attached to this carbon, or sorry, the 4 things attached to this carbon are the O's, a hydrogen, and this other carbon. Over here, that hydrogen and other carbon are still there. They are not involved in every case here. So in this case, we had two H's here, and they're still there. They never went anywhere. Okay. On the last one, I want you to try this one. It's slightly different because they're not separate things, right? We have a cyclic acetal here. So, but play the same game. Break this thing apart. Here's the acetal carbon, right? You identify it because it's the one with two ORs on it, right here. Add your water molecule, so draw water in here somewhere, right? Maybe in here somewhere. And then you make a bond between this carbon and the water's oxygen, right? That water needs to lose an H. We put it on the neighboring O. We break this bond, right? Just like we've been cutting off the alcohols, we're going to cut this one off. And then the carbon needs to make a second bond to that water molecule to give you the carbonyl. The oxygen of the water needs to lose its other H, and it goes on the other oxygen, and we break this bond. So what will I get when I'm done? How long will the aldehyde be? It's just like this one up here. It's going to have two carbons in it, right? 1, 2. This one didn't get involved at all. It's still there. It's not participating. So it'll have two carbons. I broke both of these bonds, and I made a carbonyl bond to the water's oxygen. So it's got two carbons, right? So it'll look just like this. It'll be an ethanal. And what would the two alcohols that cut off be look like? They're not ethanol and methanol, or they're not two cyclopropanols. They're actually connected to one another, aren't they? So I'm not releasing two alcohols. I'm releasing one that is a diol because they're connected to one another. So I break this bond and this bond, and I end up with this 2-carbon dialcohol, right? So I would get the ethanal over here, and then a 2-carbon diol, right? Just like this is 1 and 2 of the piece that gets cut off, right? They're not separate from each other. If this bond wasn't here, it would be 2 methanols, but they're connected to each other, so I get a diol.
I have a quick question. Does that carbon always go to the water's oxygen?
Yes.
Always?
Yes, so the acetal carbon will always make a single and then a double bond to the water's oxygen, which is the exact opposite of how we made this molecule in the first place. Remember, it was a carbonyl with 2 bonds, and then it went to 1 bond, and then it went to no bonds, and that O left with a couple H's to make water. So it's the exact reverse of that process. Okay, we'll do more of these after class if you guys want a lot of practice. Okay. All right. Any questions on this?